Welcome back to the deep dive. Today, we're tackling a really critical question, one that I think keeps a lot of people up at night.
For sure.
When you implement something new, a new strategy, a new process, how do you actually know if the results you're seeing are, real and statistically significant?
Or if you just got lucky.
Exactly. Or if it's just random noise. So we are going to dive deep into the science of comparing multiple averages all at the same time.
And that's the whole mission, right? When you're just comparing two things, it's pretty straightforward.
Method A versus method B, simple enough.
But the second you add a third or a fourth option, the math gets complicated really fast. You need a powerful tool for that.
And that tool is ANOVA.
Analysis of variance?
Yeah.
Or ANOVA. It gives you a rigorous framework to test if the averages across 2, 3, 10 populations are actually equal.
Okay, let's unpack this. I think the best way is with a good high-stakes scenario. So imagine a company, let's call them Chemitech. They make these specialized filtration systems, and they've come up with 3 slightly different assembly methods. We'll just call them A, B, and C.
Right.
They need to know which one gives them the highest mean number of products per week. And this is huge because if they just pick the one that looks best in a small test,
So that difference is just random fluctuation.
they could standardize a mediocre process across their entire plant. That's a potential loss of millions in efficiency.
And this is why the structure of the investigation, the design, matters even more than the final calculation.
Okay, so before we even get to the numbers for Chemitech, we have to talk about that foundation.
Experimental design.
Yeah,
You really have to know the difference between two main types of studies.
which are?
Well, first you have an observational study. That's where you just, watch and record data as it happens. No interference.
Like studying diet and lifespan in the general population. You're not telling people what to eat.
Exactly. But for what Chemitech is doing, for true optimization, you want an experimental study.
That's where you're actively in control.
You are. You control the levels of one or more factors to see exactly how they influence the outcome, the response variables. That control is what lets you confidently claim cause and effect.
And since Chemitech is controlling the assembly methods, that's an experimental study. Perfect for ANOVA.
Perfect.
So let's use their example to nail down the terminology, just so we're all speaking the same language here.
Good idea.
The thing Chemitech is investigating, the assembly method, that's the factor.
Right.
The specific versions A, B, and C, those are called the treatments or the levels.
Mm-hmm.
The outcome they're measuring, the number of units produced per week, that's the response variable.
And the objects of interest. The people they're actually studying.
Those are the experimental units.
Mhm.
In this case, the 15 employees in the study.
Now, here's a detail in the setup that is so crucial and so often overlooked.
Okay.
Chemitech didn't just pick their 15 best workers. The source material is very clear on 2 key randomization steps. First, they randomly selected 15 employees from their workforce.
Okay, that makes sense. A representative sample.
And second, they randomly assigned those 15 people into 3 groups of 5, and then assigned the treatments A, B, or C to those groups.
Why go to all that trouble? I mean, why not just let the first 5 people who show up be Group A?
Because that's your insurance against bias?
Yeah.
What if the people who volunteer first are also the most motivated?
Oh, right. Then if method A looks good, you don't know if it was the method or the highly motivated workers.
Exactly. Randomization spreads out all those other variables, skill, fatigue, experience evenly across all 3 methods. It ensures that any difference you see in the end is really due to the method itself.
And that's what's called a completely randomized design.
That's it. So with that solid design in place, we can finally get to the logic of one-way ANOVA. And it tests a very specific hypothesis.
The null hypothesis, H0. The assumption you make until you can prove it wrong.
Precisely. The null hypothesis is the statement of no effect. It says all the population means are equal. So the true average production for method A, B, and C is actually all the same.
And the alternative.
The alternative hypothesis, HA, says that the methods do matter, that not all the population means are equal.
So at least one is different from the others.
And that's a crucial statistical insight. Rejecting the null hypothesis doesn't mean A is better than B and B is better than C. It just means that at least 2 of the methods are different. The factor matters.
Got it. Okay, let's look at the actual sample data from the Chemitech test. They ran the experiment, and here's what they found for average weekly production. Method A had a mean of 62. Method B was the highest at 66. and method C was the lowest, down at 52.
Okay, and the overall average.
The overall average across all 15 workers, the grand sample mean was 60.
So you can see the differences right there.
66 is obviously higher than 52, but the core question ANOVA answers is this. Is that difference big enough to be real, or could it just be a fluke?
Just random variation you'd expect to see, even if the methods were all identical.
Right.
Now, before we run the test to answer that, we have to check 3 critical assumptions, just to make sure our model is valid.
Okay, what are they?
First, the response variable, the production numbers, should be normally distributed for each method. Second, the observations have to be independent. One worker's output can't affect another's.
Makes sense.
And the third one is key. We assume the variance is the same for all 3 populations. It's called homoscedasticity.
So you're assuming the consistency is roughly the same, even if the average is different.
Exactly. Think about it. If method A was wildly inconsistent, 1 week 40, the next week 80, while method B was always between 65 and 67, then comparing their averages is almost meaningless.
That makes perfect sense. Okay, let's get to the real aha moment, the mechanism that makes ANOVA so elegant.
This is the good part.
The whole technique really seems to hinge on breaking down the total variation in the data into 2 separate parts.
Yes, partitioning the variation.
So if the variation that's caused by the different assembly methods is large compared to, the general random noise of the factory floor,
then you can be confident something real is happening.
then you can reject the null hypothesis.
Exactly. ANOVA takes all the variation in the system and splits it. We calculate the variation due to the treatment. We call this MSTR, mean square, due to treatments.
Okay, MSTR.
And we compare that to the variation due to random chance, which we call MSE, or mean square error.
Let me try an analogy. Is MSTR sort of like the signal you're trying to detect?
That is a perfect analogy, yes. It measures how far the group averages. 66, 62, and 52 are from the overall grand average of 60. If the methods really pull the results in different directions, that signal will be strong.
And then MSE is the noise.
Precisely. It's the variation within each group. Why did the 5 workers using method B get slightly different results? That's the background noise, individual differences, someone having a good day, a bad day, stuff the method doesn't explain.
The error?
The error or the noise.
So the F-test is essentially just a signal-to-noise ratio. You're just dividing the signal, MSTR, by the noise, MSE.
That is the core logic. If your calculated F ratio is small, maybe close to 1, it means the signal is no louder than the noise.
And the differences are probably just random chance.
But if that F ratio is very large, it means the signal is drowning out the noise, and that's strong evidence that the treatments themselves are causing the difference.
Okay, that's a very clear way to think about it.
And here's the kicker. If the null hypothesis is actually false, if the methods really do differ, then MSTR isn't just measuring random error anymore. It's measuring the real systematic difference plus that random error.
Which makes it get much bigger.
Much bigger. It causes the MSTR to spike, and your F ratio shoots way up.
All right, let's get to the conclusion for Chemitech. They're betting millions on whether the signal is loud enough. What happened?
Well, calculations were run on the data from the 15 employees, and they found that the MSTR, the signal, was 260.
Okay. And the noise, the MSE?
The MSE was much smaller, only 28.33.
So when you calculate that F ratio, MSTR divided by MSE?
You get an F ratio of 9.18.
Wow, okay. That seems high. So how do you decide if it's high enough?
You can use a couple of approaches. With the critical value approach, at a standard 5% significance level, the cutoff value is 3.89.
And we got 9.18.
Way over the line. So we reject the null hypothesis.
And what about the p-value?
The p-value was about 0.004, which is much, much smaller than our significance level of 0.05.
So again, a clear rejection.
A very clear rejection.
Oh.
The definitive result for Chemitech is that they have statistically significant evidence that at least one pair of their assembly methods produces a different average output. The method really, truly matters.
This is great. This is where we move from the academic exercise to the real-world application, because ANOVA isn't just a textbook tool.
Not at all. It drives major business decisions.
So where else should you, our listener, be thinking about applying this? I mean, think about a marketing department.
Oh, absolutely.
They could use ANOVA to compare the mean return on investment from, say, 4 different advertising methods: TV spots, flyers, social media, magazine ads.
And they need to know if the differences are real before they allocate a $1 billion budget.
Exactly. Or what about in supply chain management?
You could be comparing the mean quality levels of components you get from 5 different vendors.
And you need to know if vendor D is actually superior or just having a lucky streak.
Right. And it's huge in HR and education, too. Comparing training methods.
In-person, online, hybrid. You'd use ANOVA on the mean improvement scores of employees to see which training program is actually the most effective. It gives management the data to make a confident choice.
And the beautiful thing is you don't need to be a math genius to do this. The concepts are what's important.
Right, the logic of signal versus noise.
Exactly, because the actual calculations are readily accessible. Tools like Excel's data analysis add-in have an ANOVA, single-factor tool, that does all the heavy lifting for you.
It'll spit out the MSTR, the MSE, the F ratio, the p-value, everything.
All of it. Understanding of the logic is far more important than memorizing the formulas.
Okay, let's bring this deep dive home. If you're going to remember just a few things about ANOVA, what should they be?
Well, first, it's your go-to method for comparing 3 or more means at once. It keeps you from getting lost in endless, messy two-group tests.
Second, its power comes from partitioning that total variation into 2 buckets. The explained part, the signal, MSTR, and the unexplained part, the noise, MSE.
Right, and that's what builds the F-test.
And third, and this is maybe the most important, the integrity of that whole test depends on a solid experimental design with randomization.
That's the insurance policy. That's what lets Chemitech confidently conclude that one method is probably better than the others.
Okay, so a final provocative thought for you to chew on.
All right.
Chemitech has successfully rejected the null hypothesis. They know that assembly method matters, but they still don't actually know which methods are different.
That's right. Is B better than A and C?
Yeah.
Or are A and B basically the same and C is just much worse?
Exactly. Knowing that a difference exists is just the first step. So what kind of critical statistical tools would an analyst need to use next after a successful ANOVA test to pinpoint exactly which pairs of means are different?
Because that follow-up step is where the real business optimization begins.